All right, so let's finally start in on some of our actual physics lessons, and we're going to talk about kinematics. So kinematics is essentially the study of movement. So kine comes from the same word as kinetic. So like our kinetic energy is moving energy. Kinematics is when objects are moving. So we're going to start going through some of this information. As we go through in your note packet, you do have a note or a page for vocab words, and you will need to fill that in at some point before the end of the unit, so all your vocab words are on one sheet. Also, we're going to skip the preconceptions page and just jump straight to the notes. As we go through, I highly encourage you to take additional notes and highlight things that you think need to stand out or make more sense to you. But we're just going to run through this slideshow, and we're not going to go the whole way through, but we're going to see how far we can get. So, kinematics is the study of motion, and we don't care how the object started moving, we just care that it is moving. So we're studying how objects move, and it's kind of like when you're driving a car. As you're going down the road or the highway, your speedometer is telling you the car's speed, so it's telling you how you're moving, and it's based on the distance the car travels in a certain amount of time. So we say it in miles per hour. In science, we're going to say kilometers per hour because we don't like the imperial system in science. And this number on your speedometer is going to be instantaneous. So that's showing you at that exact moment how fast you're going. It doesn't tell you if you're speeding up or slowing down. If you're going up a hill, then your speedometer at any given point in time is probably slowing down. As you're going down a hill, it's probably speeding up. But it's telling you at that exact moment that you looked at it, what your speed is. And so to find the average speed of the trip, you actually have to look at your odometer. So your speedometer is telling you how fast you're going or the speed that you are going. Your odometer is going to tell you your total distance traveled. And then also newer cars will tell you how long you've been doing a total trip. And so using those, you can determine your entire average speed. And while speed is going to tell you how fast an object is moving, it doesn't tell you what direction. So because it's just that number, it's called a scalar quantity. So speed, distance, and time are all considered scalar. That means that we could point out exactly what it is somewhere on a number line. And our scalar quantities have magnitude, which is the number. So the amount or the number that we associate with it, but it doesn't tell us a direction. So you can say that you're traveling 100 kilometers per hour for 4 hours, and you could look at your odometer and say, okay, well, so we've traveled 400 kilometers. All of those numbers all have a magnitude with them, but they don't tell you a direction. So we don't say we went 50 kilometers north and then 20 kilometers east. We don't say anything like that. We just say, here's our total scalar value. But in physics, we are usually concerned about what direction you're going because it makes more sense for a lot of the things that we do. So we have numbers with a magnitude and a direction, and that is considered a vector. So if we have like 5 miles per hour east, we have a number and a direction with it that is considered our vector quantity. And we will use this with position, displacement, velocity, and acceleration, and we're going to write it as the magnitude of the units, so your number, and then you're going to put a direction in those brackets so that we know which way that number is going. When we write it, you're going to put this little like half arrow on top of whatever variable you're using. And these slides are going to call it a vector hat. So we're just going to go with it because there are a lot of really great weird puns I can do to make you remember that. So we're going to look at this V with the arrow on top of it as wearing its little vector hat. And that's telling us, okay, so the velocity in the vector form is 4.2 meters per second heading east. So this is telling us all the information we possibly need to know about what is happening with that number. And then the way that they want you to remember to put your hat on your little variable is to say vectors are going places because they have a direction. So they have to wear their hat. And they're probably going somewhere fancy. So it's a top hat. Anyway, we have a ton of different types of vectors in physics. We are going to see them throughout everything that we talk about this year. But in this unit, we're going to be focusing on your position, displacement, velocity, and acceleration. So where you're at, how far you went, how fast you were going, and then how fast you were slowing down or speeding up. Now this slide you're probably going to want to pause on to fill in the boxes on your notes. We have a couple of different things that we're really going to start looking at in this video. So you have your position, where we have D with a top hat on it, and that is a position of an object relative to a reference point. So it's like those "you are here" maps. If they didn't tell you where here was, it doesn't make any sense. So we need to have a landmark or a reference point associated with it. You can't say "I am here" and expect someone to know, but you can say "I am 5 miles east of Hucks." That is something more that we can associate a reference point with and understand exactly where you are. So in this example, we have the position is 5 meters and then east. So we have our vector symbol on our D, which means that we are going to have a number associated with that direction as well. And then we have displacement. So displacement, we use our delta, just triangle, and that means change. So we're looking at the difference between where we start and we finish is our delta. And the delta D with the hat on it is telling us the displacement. So how much things have changed in our distance from where we started to where we ended. So in this point, we have taken our little blue person, and instead of being 5 meters east of the reference point, they're now 7 meters east of the reference point. But the person only actually moved 2 meters east. So we have our change in position, so our delta D is 2 meters to the east. So now we're going to look at this street scene, and this is in your packet. It's going to help us kind of put all these ideas together between position and displacement. So we are using the reference point for these examples as the cinema. Fancy, remember we're wearing our top hats. So we are using the cinema as our landmark or reference point, and they say you exit the cinema after watching a movie. So what we talked about in class today was you're leaving the movie theater, you just watched Mulan, you're trying to decide whether or not it really needed the songs in it because people are really angry that the real version doesn't have songs. Apparently Mushu's not in it. I mean, there's so many things to ponder. So you're standing right outside of the cinema right after the movie. So what is your position? Now we're relative to the movie theater. So our position is actually just 0. But remember, we have our position including a vector. Since we're not anywhere different than our reference point, we don't actually have a direction. There's no point in saying 0 meters to the east or 0 meters north. So we're just 0 meters from the reference point. This is also the point where I want to remind you that every single number you put down in this class needs to have a unit. If you can't tell me a unit, then the number is useless. I like to say no naked numbers, dress it up, get ready to take it out on a nice date, but do not let it just walk around without making any sense. So we're standing right outside our reference point, so our position is 0. How far have we moved from the reference point? Well, 0. Now, our position, which would normally include a distance from the reference point in a direction, has our vector hat on it. Now, the total distance that we go, though, with distance, we don't care about what direction. We just say, okay, my distance is 5 feet. That's it. So we don't have to have the vector on top of it. So now we've walked out of the movie theater and gone 0. Now we are going to go write a sternly worded letter to the people who created Mulan and tell them our opinions. So we have to walk to the post office to mail it off. We've started at the movie theater, which is our reference point, and then we move over to the post office. So our new position is 23.4 meters east of our reference point. Now we have to make sure that we're including east in our top hat because we're talking position. The total distance we've traveled from leaving the cinema in our first step to the post office is also going to be 23.4 meters. Again, though, distance is just how far we've gone. We don't care what direction. Your position includes a direction. So after writing your sternly worded letter and mailing it off, you go back to the movie theater because you left your keys. So after walking back to the movie theater, we need to know your new position still relative to our reference point. Position needs to be next to a reference point, and we started at the cinema as a reference point, so we still have technically gone 0. It's like if the Flash travels around the world and you blinked and you didn't see him move, it doesn't look like he moved. So his total position vector is still 0. But the distance you traveled, you started at the cinema, you traveled a distance to the post office, and then you traveled back. So we have to take 23.4 meters to the post office and 23.4 meters back to the cinema and add them together to get our total distance traveled of 46.8 meters. Now, after going to get your keys, you realize that you're a little hungry. So we walk to the bakery. Now, the bakery is how far away from our reference point. So we're going, the total distance from our reference point is at 23.4 meters to the post office, plus our 37.7 meters from the post office to the bakery. So our new position with our top hat on it is 61.1 meters east of our reference point. Now the total distance we've traveled, though, we walked from the cinema to the post office, back to the cinema, back to the bakery. So we're going to take the number we had from earlier for our total distance and add in our new position value. So you're going to get our total distance having been 107.9 meters. So this is the distance that your Fitbit is going to track for you. If you walk around a track 800 times wearing a Fitbit, it's going to count every single step. But if you look at a GPS, it's just going to be like, hey, you just started where you stopped, or you stopped where you started. So we need to make sure we remember that position is relative to a reference point. So every time I ask you what position you're in, it is relative to where I'm asking you to tell me from. So if I say, what is your position relative to Trico, you're going to tell me how many miles in what direction you live from Trico. Okay, so now we're going to talk the difference between distance, position, and displacement. We're actually going to change our reference point to be the post office. So now our reference point is the post office, but we still are going to follow the same path we did earlier. So we're going to leave the cinema after watching Mulan, debating whether the music really does make our life better. So we've left the cinema. What is our position? Position is relative to our reference point, and we set our reference point as the post office. So now our position is 23.4 meters west of our reference point. And the total distance we've traveled is still going to be 0. We didn't start at the post office and then walk to the movie theater. We started at the movie theater, which happened to be 23.4 meters west of our reference point. But our Fitbit is still telling us we didn't do anything. So now we're walking to the post office. So what's our new position? Our position is relative to where our reference point is. So 0. And because it's 0, we don't really care what direction it's in because it doesn't matter. But our displacement from where we started is 23.4 meters east. So our total change from our starting point at the movie theater to now the post office is we've walked 23.4 meters east. And our total distance we've traveled, so our distance is what our Fitbit is measuring, is at 23.4 meters. And our Fitbit doesn't care what direction we're going in. So now we're going back to the movie theater again. So our new position, again, only relative to our reference point, is going to be that 23.4 meters west of our reference point. Our displacement, so how far we've moved from where we started, we walked from the movie theater to the post office, back to the movie theater. We've technically displaced 0. We are still exactly where we started. And the total distance we've traveled is the distance from where we started to the post office and back. So we're going to add that total distance together to get our 46.8 meters. Now we're walking back to the bakery because, again, we're just hungry. So our new position relative to our reference point at the post office is going to be 37.7 meters east, because that's where we are against our reference point. Our displacement, or how far we are from where we started, is actually going to be the distance from the cinema to the bakery, which is that 23.4 plus that 37.7. So our displacement is 61.6 meters east. And again, because we have the direction on our displacement, we are putting that top hat on it, and we care about what direction we've totally traveled. Now, what's the total distance we traveled? We started at the cinema, went to the post office, went back to the cinema, and then went to the bakery. So we have to have all those distances together to see what our Fitbit would say, and it's 107.9 meters. Now, we walk all the way back to the cinema. So, start at the movie theater, post office, movie theater, bakery, movie theater. We are still only 23.4 meters west of our reference point. And our displacement from where we started to where we finished is just going to be 0. But the total distance is every single step that we've taken added up by our Fitbits, and that's 169 meters. So we just want to make sure that we keep clear. Displacement is our total change from where you stop from where you start to where you stop, and the total difference between those 2 points only. And then, if they are the exact same, it's going to be 0. It's like when the Flash runs around the world. No one really knows if he did it, so his displacement was 0. And that is the end of our first lesson. Look at us go. Please make sure to fill that in your notes. Make sure you highlight everything that you need to highlight, and I will see you guys in class.